Okay, hello everyone. So today's topic of the webinar is the best practices for modeling your data with graph database, right? So what I will talk about today is the best practices to design your graph schema. As we all know that uh, firstly, actually, let me introduce myself. I'm Xinyu Chen. I'm the director of customer solutions at TigerGraph. I've been with the company over 7 years, and during the 7 years, I actually co-authored the GSQL query language. So I also lead a lot of the largest solution projects, and also my team developed the graph algorithm library. Yeah, so that's my background, and today I will talk about the best practices for the schema design. So schema design is very important because it's kind of is the foundation of your Tiger Graph solution, right? Usually it is the first step to to build your Tiger Graph solution. So from there we define what vertex types we have, what edge types we have, right? And also what are the attributes on the vertex and the edges. So it is very important because it is a good schema design can make sure you have the best query performance, and also it minimize your system resource consumption, right? So usually schema, to define a graph schema, we need two informations as it is illustrated in this diagram here. So we need two things. First, we would need the input data format, right? Whatever data you have in your data source, the data format actually largely impact how your graph schema look like, because you cannot define an edge across two tables, right? Otherwise, you won't be able to directly ingest them. And and also another thing we need to think about is the use case, because we always need to make sure your graph schema serves the purpose of your query use cases. We want to design the schema in a way that makes sure that most of your queries runs pretty fast, right? Okay, that's the two things to consider when we design the graph schema. Here are a list of topics I want to discuss today, right? So it includes like what's the rule of thumb, what can be the vertices, what can be edges, how to define your edge type, undirected, directed, or reversed, the granularity of edge types, attributes. Should I define attributes, vertex attributes, or should I define vertex, or should I use a secondary index for the search? Or when should I enable ID as attribute? How should I model the time series in the graph? How can we model the multiple events and the transactions between two entities? And how can we model the graph in a way it can store your query result and also support the utilization of the data scientist library, right? And also how in complex situations, how do we design the schema based on your specific use case, right? So these are the topics I will discuss today. And the first question is, what can be vertex and what are the edges, right? So usually this is a pretty straightforward. Any entities or abstract concept can be defined as vertices. For example, it can be person, it can be user, company, account, product. Any entities or concept can be vertex, right? And any relationships can be defined as edges. For example, two employees, they are co-workers, right? One employee works for a company, one company is controlled by another company. All this kind of relationship between two entities, they can be defined as relationships or edges. Okay. And So here are some examples how they look like in the actual graph, how entities are connected via the relationships. And the next question also is very important question is how do we choose the edge type? Because from integral graph, there are three edge type options that are the undirected edge, directed edge, and the directed edge with reverse edge. So each of them has their own pros and cons, and we want to make the decision based on our specific use case, right? So let's get started with undirected edge. Undirected edge is an edge connects to between two vertices that you can go both directions. You can traverse from A to B, and also you can traverse back from B back to A, all within the same edge type because there is no direction, so you can go both ways. And for directed edge, you can traverse from A to B, but you don't have an edge from B back to A, so that there is no way we can go back to A from B. So that's directed edge. And then we also give the users an option to enable the reverse edge. That means between two vertices A and B, we have directed edge E1 from A to B, and then we have the reverse edge type E2 connecting from B back to A. So E1 and the E2 here are two different edge types, but they are symmetric. That means if I remove E1, the corresponding each edge under E2 will be removed as well. If I update E2, the corresponding edge under type E1 will be updated too. So there is always a, a symmetric edge going there under a different type. So how do we make the decisions? When do we choose different options and based on different cases, right? So for undirected edge, so the advantage is really it is very simple to write your queries because you don't have to think about the direction you are going. You just um, you just use whatever edge type you want to traverse between two vertices, right? And you usually it can be used like for undirected relationship. For example, let's say a Facebook friend, right? There's no direction. It's not like a Twitter that there is a following direction, and also. It is recommended like as long as your source vertex type and target vertex type they are different, it's recommended to use undirected edge because at that point the directional info is already encoded to the source vertex and target vertex. So you already know the direction, and also it makes your query writing easier. Later I will give you an example, you will get it there. Okay, so but the cons is it doesn't carry any directional info. So that means in the case both source vertex and target vertex are having the same type, there's no way you can tell the direction. I will give another example after this slide too. It's okay if you get it here. Okay, so and for directed edge, the process is like it is very memory saving because you only store the edge once for the source vertex, right? But so you only use half of the memory, but it cannot traverse back from target to source. So we really need to think things through, but we decide we only define the directed edge without the reverse edge. And we should be 100% clear that in the future we will never traverse to A from B. Okay, and then we have directed edge with reverse edge. The advantage is like it's very flexible to traverse in a designated direction, right? You can go any directions with different types. But the cons is really you need to maintain and remember two edge types, and then you always need to think about if you are using the correct edge type when you write the queries. Okay, so now let's look at some examples to see what are the actual differences I just talked about. Okay, so here is a query writing example showing the difference between the undirected edge and directed edge with reverse edge. let's assume we have a use case, like we have users, and the user may has an email address, right? And then now we want to ask questions. Okay, find the user shares the same email address, right? Then if we define this as an undirected edge, like a valve, right? Then we just need to write a two-hop query. It's very straightforward and easy. But if we define it with a directed edge with reverse edge, you can see the query will become longer than the undirected edge, right? Because if we define it with a directed edge with reverse edge, you always need to think about the direction. From the user to email, use this type, and from the email, go back to the user, you need to use the reverse edge, right? You always need to think about the directions, and you need to maintain different types. So the rule of thumb is really, again, if your source vertex and the target vertex are under different types, please use undirected edge. That will make your life a lot easier. Okay, I see some QAs. Yeah, I will talk about vertex and attribute. Yeah. So so there is a question about, does directed edge plus reverse edge use more memory than undirected edge? The answer is they use same amount of memory. Okay, because under the hood, the only difference I would say is the at the metadata level, right? The reverse edge would maintain two different edge types, but in the actual data, the data level, storage level, right? They are the same. We just store the same edge for both the source and the target node. Okay. Okay. And now in this example, I will talk about what's the difference between in certain cases that undirected edge doesn't work, but directed edge plus reverse edge can solve your problem. So let's assume we have a graph of companies. Each node here is a company, and the edges between the companies are the ownership relationship. Like company one owns part of company two, right? And in this graph, we want to ask questions. Okay, given the company, I want to find the ultimate parent company of the given company. That is, for example, if I give given company C4, I want to find the ultimate company C1. However, if we imagine, if we define the edge as undirected edge, and we start from C4, and we see C2 and C7, oh, we suddenly lost the direction. We don't know if C2 is the parent company or C7 is the parent company. We don't have that info anymore. Then we cannot answer this question with undirected edge. However, if we define the edge in the type of directed edge with reverse edge, then it's much easier to answer it. Then we just follow the red edge that has parent company edge all the way to the top. Then we should be able to find its ultimate parent company C1 in this case. But again, you can see that in this example, both source vertex and target vertex, they have the same type. So in this case, if direction matters, then we need to define it in the directed edge and reverse edge way. If direction doesn't matter, then again, we should use the undirected edge. Okay? So that's the difference between undirected edge and the directed edge with reverse edge. So here is another thing should be very interesting to discuss. It's like sometimes between two entities, there can be multiple different types. For example, between two persons, they can be co-workers, they can be relatives, they can be friends. In that case, should we define a specific edge type for each different relationships, or we should combine them together and then differentiate the type based on some string type attributes? So each of them has their own pros and cons, okay? So for the design on the left-hand side, it is very efficient when you want to traverse a specific type of relationship. For example, now I only want to get all the friends of a person, right? In that case, adopting the design on the left is much faster. The reason is the storage under the hood, actually each edge type is stored in different offset. So if you want to traverse a specific type of edge, the system help you to identify the starting point of the offset of that edge type very quick. So you don't have to scan over all the edges in order to find a specific type. So that means if you have finer granularity of the edge types and you want to traverse a specific type, it is very fast, right? And the plus, you don't have to store the string as attribute. That can save you some memory as well, right? But the cons is like if you have to traverse all the types, you specify each of them in your select statement. It's kind of like a pretty makes your query less concise, right? But if you look at the on the right hand side, it's like the process is easy to traverse all relationships. However, you have to store the type as a string attribute. It takes actual memory, and if you want to traverse a specific edge type, you need to do full edge set scan, and also you need to you know do string comparison, which is slow, right? So usually we would adopt on the approach on the left hand side. Okay, so the next topic I want to discuss is like a suite. So given the, yeah, let's look at the table in the center of the slide. Okay, so let's say we have a product table. Product may have color, brand, type, and price. How do we make the decision? Should the column color be vertex, or should it be an attribute, or should it be an attribute with a user-defined index? Right? Because if they are just plain attribute, now I ask a question, okay, give me all the red colored products, is actually a full table scan, or we need to scan all the products in order to find those are in the red color. It's going to be, even we handle everything in parallel, we can handle like 100 million vertexes in 1 second, but still we don't want to make our operation so expensive, right? So in that case, when you frequently query about us, we want to do filtering and query for some specific attribute, usually the better choice can be defining it as a vertex or a secondary index. Now let's see what's the difference between them, right? So this is an example like how we define brand, color, and type as a vertexes. And in this case, if you want to find all the red colored vertex, you just need to start from the red vertex and find the associated products, right? It's nothing but a graph traversal. It will be a lot faster than the, a full table, a full vertex type scan. And another option is we can also enable the index option from Graph Studio. And also we have corresponding grammar syntax for you to enable the index from the GSQL console side. So the user-defined index or secondary index are a critical feature that can enhance the performance of a database system. Index allow the user to perform fast lookups on non-key columns or attributes without a full-fledged scan, right? So you can see that on the architecture diagram on the right, you can see the index data is also stored distributedly together with the graph data. That means it will stay together where the data is stored for a specific vertex, right? For example, all the attributes and the edges of vertex A are stored on server 1, and so will its index info stored on server 1. That guarantees we minimize the shuffling during the queries, right? So once the index is defined, you can use it in your filtering just like a regular where clause, right? Then the system will be able to tell, okay, now your filtering condition is based on some indexed attribute instead of plain attribute. Then it will utilize the index system automatically. And the index is stored in a cache, a configurable sized cache in the system. And from the cache, you can like so that means you won't like use very excessive size of memory in order to speed up your search. Okay, so that's a secondary index. And here, I want to show you a few benchmark results of the secondary index. Okay, so this is a low cardinality graph, and you can see up to 50%. That means one index value may cover 50% of data. Like so we run the test at the 25% level, and also again at the 50% level at a different scale factor of data. So at the left up corner, this is a scale factor 100, and the right lower corner is 3000. So we run the test on different size of data, and you can see we have superior performance with the index than without the index, up to 50% of the selectivity. That means one index value may cover 50% of data. And the index still give you better performance. Okay, and here is another chart. So if we have a medium selectivity graph, that means we the medium cardinality graph. And this, again, we run the test on different skill factors, and you can see there is a cross point that the performance with and without index are the same. And after that, without index is actually faster. The reason is at a medium cardinality graph, that means we have reasonable large number of index values, and select like one index value when it's over 25%, then it is faster without the index than using the index, right? So that means in our real life use case, we need to have some knowledge of our graph so that when we build the index, we should know, okay, each of the value will cover less than 25% of the data, then there is a it is worth to build the index. Otherwise, we need to think twice. Will that really speed up your query performance, right? So based on the benchmark, we can make two conclusions. So first one is the low distinct value of attribute will make your index looks better. And the low selectivity query on the attribute will make your index looks better. That means you have lower distinctive value, and also the coverage of each value is lower. Usually that can make your index looks better. Okay, that's when we use the index. And then now the question is, now we know the way of defining vertex as index. Also, we know like we can build the secondary index over the attribute, right? Then how do we make the decision? So there are 4 points to that, right? First, secondary index supports range predictions, while index vertex doesn't. So if we want to filter by some continuous values, right, then secondary index works better, especially float values. You cannot just define the float value as your vertex ID, but secondary index works pretty well on that. That's the first thing to think about. And the second thing is vertex index may potentially create a hub node, and the hub node is actually not very efficient, but the secondary index is more scalable. No matter how large your data is, it only stays in the limited size cache there. So you won't make your graph extremely large or having to touch too much of the data on the graph. There are more operational or overhead for the user and maintain the indexes, right? Then that means with the index, you have extra piece of the in the schema, and you have to maintain the indexes. And then the last thing is index. So creating a vertex would have a better performance over non-continuous values, because the vertex is it does like a massive parallel traversal, and also is in memory all the time, right? But obviously indexes would use less resources, therefore it may not as fast as vertexes, but it's more resource saving. Okay. Okay, I just found a question. If I actually come across line number, so I'll read it for you. If there was a question in the chat. So if you have an attribute that is common across a large number of entities, like color, then consider an index. Otherwise, it is more a unique value. So, okay, I guess that's not a question, right? Okay, let's move on. Right, and now so we just discussed the index, right? And now we also have an option in Graph Studio and of course in GSQL console as well to check this as attribute after the ID definition, right? So the reason we have this checkbox is by default, this as attribute check option is disabled. When it is disabled, the ID value is not accessible from the query side. Therefore, like as attribute needs to be checked when the ID values are used in the query logic for non-printing purposes, such as like string concatenation or some value comparisons. You must wonder why don't we need to access the query value in the graph? What's the motivation to make the disable by default? So that needs to we need to discuss what's the underlying storage look like, right? So for the data under the hood integral graph system, we have roughly 3 types of data, right? First one is the ID service. That's what we want to talk about today. Is the ID service is a bidirectional external ID to internal ID mapping. That means in the graph, in the actual graph, vertices and the edges, they are actually stored in the internal format, right? Internal ID format, which is the integer. That is one major reason why Tiger Graph is so fast, because integers can be further compressed, right? There are algorithms to compress those integers, and the integer is obviously more efficient than strings, right? And also, like we don't have to repeatedly store all those long string IDs inside the graph, which also is very redundant and resource consuming. So that's the reason why we have this ID service. So we only store the string ID value once and then map it to an internal ID, and all the vertex and the edges and in the graph, they are in the integer type. Okay, so when it is used, so when we query when we run the query through the RESTful endpoint, and then we also pass some vertex ID as the input, then in this case, the GSE, let's say, the request comes this way, right? And with some ID to be translated, and the GSE will help you to translate the ID from the external ID to internal ID and send it to GPE. GPE as a graph process engine actually is where we run the query, right? And then GPE knows, okay, oh, these are the vertices you want to traverse, right? And after translation, GPE knows where to start. And then after running the query, GPE also prints some result with IDs, but of course, internal format, right? Because GPE knows nothing about the external ID. And again, send the result with the internal ID format to GSE, GSE translated, send to RESTpp, and then we return the result to the user, right? So you can see during the query process, as long as you don't use the actual vertex external ID inside the query logic, you don't need it at all, right? You have GSE to host the mapping for you and do the translate from the parameters and also translate the IDs in the result. So as long as you don't need to use the actual external ID value in the query, you don't need to enable that as attribute option. Okay. Yeah, so by doing this, actually you don't have to store the external ID string value all over again inside of GPE where graph data is hosted, right? Then because you already stored it in GSE once, that's why as attribute is disabled by default. Okay, so as a conclusion, IDS, the ID service, the bidirectional mapping, right, can handle the requirements of using vertex ID as a query parameters and also printing vertex IDs as a query result. So for parameter purposes and printing purposes, you don't need to access the value from the query side at all, because the IDS will handle that for you, handle the translation for you. And for as a unique identifier in the query, you don't need a string value either, because we can use the internal ID in the query as the unique identifier of vertices, right? And so that means the third point, as attribute is only needed when the ID value is needed for the purpose other than the above, not for unique identifier reason, not for printing reason, not for parameter reasons, some other reason. For example, you want to concatenate the string, right? We have no options but taking store the value as attribute. And so disabling as attribute is more memory saving. Okay. Let's see. Can you combine two indexes? Just for example, your business primary US. Then we create a vertex type US, and then the rest as the regular index for non-true index method. The rest as non-US vertex type. I'm reading a question in the Q&A. Can you combine two index methods? Yeah, maybe let me leave all of this to the end for smooth video recording. Okay. Okay. Then so now this is how do we model time in the graph, right? So because sometimes again, like when we want to query a specific, like I say, for example, we want to find all the products produced within the same period of time, right? In that case, we can, we don't want to do full vertex type scan, but so in that case, we can also define time as vertices, also serving as indexes. But we can we can build the like secondary index for this purpose as well, right? And if you want to build them, so the point here is like if you want to build a time as a vertex type, you can actually go multiple layers. So in this case, if you want to say, I want to search for the products that are produced in the first 15 days of February 2018, you can actually start from year of 2018, traverse to February, and then the first 15 days, and then find out the products produced, right? This actually traverses only very tiny amount of vertices in the graph. Okay, and this is a very frequently asked question. So for example, because right now, one feature of tag graph is like it only allow you to have one edge of one type between two vertices. So under one edge type, between two vertices, you can only have one edge instance under that type. Okay, so because that, like, so for example, if in this example, let's say if two users has multiple transactions between them, right? Then how do we model it? How do we define the schema? Then we have two different options, right? We can define each event transaction event as a vertex. And alternatively, we can also aggregate everything into one edge. For example, we can store the dates as a list. We can also aggregate the values into attributes. For example, the last transaction date, first transaction date was the total amount of the transactions, right? So what's the pros and the cons between each two method? So the first one is like if we define the transactions as event, then it's very easy to do transaction level analysis. Such for example, if you want to find this transaction communities or given one transaction, you want to find similar transactions. For example, you want to do anti-fraud and your anti-fraud use case is actually at the transaction level, then we better define it as transactions, right? And also, but the thing is, it will use more memory because you need to define two more edges for every each transaction, and you have to maintain every transaction as vertex. right? So and also the user becomes 2 hops away. It becomes more a little bit more difficult to analyze the relationship between 2 users, right? And the design on the right hand side is really like because you only use one edge, it will significantly use less memory, and it takes fewer steps to traverse between the users, right? But one thing is, if you only use the aggregated attributes, we may lose some info. Usually, we don't want that to happen, right? But in order to prevent from losing info, we can also store every info of every transaction in a container type. For example, list or set, right? But in that case, a container type of attribute usually performs slower than scalar type of attributes. For example, if you want to run frequent update, frequent update over the container type attribute will significantly makes your query performance slower. Okay, so usually actually in this case, the design on the left hand side is a lot more frequently used. Okay, and right. So other than all the data that is all the types we defined based on the input data, right? Because I mentioned in the beginning, usually we define the schema based on 2 things. One is the input data format, and the other one is the use case, right? And other than the schema type, we define based on the input data info. We can also define some derived types to store your computational result, or in order to support your like say data science library utilization, right? So in this slides, it is an example, like say, if a patient has 2 consecutive claims within short period of time, then we can infer there is a referral relationship between the doctors, right? And based on doctor, we can run a page rank over the referral network we created from the previous analysis, right? And in this case, in your schema, you need to define some edge types based on your, um, uh, to store your analytical result and support your future query utilization. And for stuff other than that, so in order to utilize the data science library for attributes, sometimes if you want to run some weighted algorithms, for example, weighted page rank, right? We need a weight attribute on the edge. And after running the page rank, if you want to say, okay, I want to store the algorithm result in the graph, then you need to define an attribute to store the page rank score. And for vertex types, you may need to define the vertex type to store the community statistics if you want to run, like say, weakly connected component or low-win algorithm. Then after calculating the community, you want to use some vertices to store the statistics. Okay, and for we may also need additional edge types. For example, after calculating the result of similarity, right? We want to connect the vertices that has a very high similarity score. Then we can also build some actual edge types based on the similarity algorithm result, right? So that means depending on what kind of algorithm you want to run, you may also want to adjust your schema accordingly, either to support the execution of your algorithm or store the result of your algorithm. Okay, and yeah, the last topic I want to discuss is like we really need to think about our use case to define the schema. Because if we look at the table here, in real life, we may have a table with a lot of wide table with many columns, right? And in this case, we have say, there's a log table, right? We have event ID, the IP, server, device, user ID, event type, and message. It's kind of event log table. And there can be many different possibilities to define the schema given all these columns, because you can just basically connect an edge between any pair of things, right? Then there are a lot of choices and possibilities when we define the schema. But what design is the best is really depends on what use case you have, right? We want to design the schema that can serve your use case the best. So for example, we can put IP in the center, we can put the event to the center, we can put a user in the center, right? But which one makes more sense to you? Then we really need to ask ourselves what we want to query, what kind of analysis you want to define, right? What's your use case? Because and usually we need to think about this because we only have limited amount of hardware resource there, right? Otherwise, we can connect everybody together, right? Then you have as long as you have infinite amount of hardware resource. But the reality is we want to design the graph schema that can minimize the memory footprint and also give you the best performance, right? So then now let's discuss what's the difference between the event-centered schema design and the user-centered schema design. So the event-centered schema design, the advantage is like what all the info of an event is one hop away from it, right? So that means if you want to run use case like on the right, for example, if you want to find the communities of event, it's very good. If you want to find the servers that process most of events given the event type, that's also pretty easy. You just need to do a two-hop traversal, right? From event type to event, and then go to the servers. Then you can answer the question here. However, if you adopt the user-centered design, then it's pretty hard to answer that, right? Because you don't, since you don't have direct connections between event and server, you don't know which event happened on which server. You cannot even, you lose that information, you cannot even answer that question, right? And also for the first event-centered design is also very good for for example, if you ask questions, I want to find the servers visited by the given IP, right? Then you just need to do another two-hop traversal and you get the answer. But it's also, yes. So, but the cons here for the event-centered design is like users are become two hops away, right? And two hops away from all the IP servers device being used by this user. Then if you want to do like a user level analysis, it becomes harder, right? So on the other hand, this user-centered design is more easy to run analysis over the users, right? But events becomes two hops away. So for example, if we want to do, say, I want to start from an input user, detect the blacklist user in k hops, that's very easy, right? Because all the users can be connected through some common stuff, right? Then it's very easy to run like a user level anti-fraud or whatever to connect the users with common attributes, right? That becomes very easy to run analysis on the user level. Or if you want to find a set of blacklist users, identify the whitelist users similar to them. If you want to run user similarity, that also becomes easier, right? And or if given two input users, are they connected with some path? Right? We want to connect some passes between users. That is also very easy if you make the schema design user-centered, right? So overall, the point I want to make here is that we should design the schema based on like where your analytic happens, right? What level is your analytic tasks is at, and then we can adjust the schema to better serve your analytical purposes. Okay, that's all the topics I want to cover for today, and let me look at the QAs to see any new questions. Okay. So I see a question from Hanbing. Can you combine two index method? For example, if your business is primarily US, can we create a vertex type US and then the rest as non-US? Right. So in that case, I feel this might not be a good case for utilizing the index, because if most of the vertices are actually inside of US, that means the coverage of index UX might be pretty high, right? And if we go back to the benchmark of the index, you can see that for even for a low cardinality, right? So if your coverage is become higher and higher, the performance difference between with index and without index will become very closer, right? So in that case, if primarily the majority of the data having value index, then having the value US, the performance gain from the index might be pretty not that significant, you know. Any other questions? Just feel free to leave in the QA. Okay. Right, and also if we want to try out Telegraph, you can just go to tgcloud.io, which is our cloud website that you can start some free instances with starter kits with all kinds of different use cases to try things out, right? You can also download our enterprise edition that is free up to 50 gig. And also you can run test drive, like we have some demos with a few billion edges loaded, and you can see how good the performances are. And also you can get certified by taking the 101 certificate and the data scientist certificate, or join the community and the questions there. Okay, and I will also talk about query writing best practice in March 23rd, and I'm really looking forward to see all of you guys there. Okay. Okay, so Carly, that's all the content I have for today. Anything you want to add?
No, thank you all so much for coming. And yeah, we have, we're looking forward to seeing you at the next part, March 23rd. And then next week, if you're interested, we're introducing our machine learning workbench. So we're really excited about this. You can register at the link. We'll send out the slides, or you can go to our website. Thank you so much, Anu, for your amazing session. And if you guys have any questions, join our community and ask them there. Thank you all so much and have a great rest of your day. And yes, we will share the recorded video with you afterwards with the slide.
Okay, thank you. Bye. Have a good day.
Thank you. Have a great day. Bye.